Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm Yogashri Pradhan, and with me here today, I have Gabriel Pedigo from Seismos. Today, we're going to discuss SPE paper 212337, constraints on pipe friction and perf cluster efficiency from the water hammer analysis. Welcome to the podcast, Gabriel.
Hi, thank you for having me.
Great. So let's just go ahead and go straight to the questions. At a high level, how does the acoustic friction analysis work from a physics perspective?
Yeah, so the way this works is whether you realize it or not, as you're pumping along, any instantaneous change in volumetric flow rate, whether up or down, is going to emit a wave in the well. Some call it the water hammer. It's just a pressure pulse that you sit in the well. And if you're sampling at a high enough rate, like higher than the 1 hertz data they typically use during pumping, you can actually see features of how that wave attenuates or loses energy due to friction in the pipe and on the bottom of the well when it reflects off the perforations. Now, what is that frequency range? We typically do the analysis at least at 20 hertz. We sample at 4,000 hertz when we are collecting the data, but we know at least 20 hertz data can see this. And once you have knowledge or can more accurately or resolutely see this energy loss, then you can go about quantifying it. If you have a expert who is very familiar with acoustics and how they would lose energy within pipe, to then model out what that friction factor in the pipe and on the perforations had to be to actually match the raw high rate pressure data then there. And once you get a match, whether you know what those values are, and similar to a step down test where you have some knowledge of the number of holes you're supposed to have down there, the hole size, and using whatever erosional models you might like whether it's David Kramer's or some you might have built yourself, you can go about predicting based on how much proppant would have been pumped when that rate drop would have occurred, what the perforation efficiency was then there. And when I say rate drops, I'm referring to anything as little as 3 barrels per minute for as little as 5 to 10 seconds, because really you're just looking for the first reflection of that pressure pulse off of the bottom of the well, which the speed of sound water is about 5,000 feet per second. Depending on the lateral length, that can be anywhere from 5 to 10 seconds. So it's a very non-invasive rate drop or occurrence that we'd be picking up on, or you'd be picking up on, to draw these conclusions from.
Awesome. So can you expand on what the deliverables are as well?
Yeah, so as far as the deliverables, the real main things we're actually measuring are friction in the pipe and on the perforations. And then we can go about turning those into other deliverables. For instance, if you have an idea of friction in the pipe, well, then you can go about solving for what bottom hole pressure is. If you know what your surface treating pressure is, all you have to do is add hydrostatic, subtract friction in the pipe, and you should get something close to what the actual bottom hole pressure is, which we've done versus bottom hole gauges before. That also can be used to glean information about pressure, obviously bottom hole, as a result of tortuosity, as well as the friction on the purse that would be leading to that, as well as obviously you've got SHMN. So if you're able to account for SHMN, you can even get down to tortuosity if you also subtract the per friction values we'd be delivering. And so that's one additional deliverable. The other deliverables would be obviously with per friction, a conversion of that into perforation efficiency, which in and of itself is meant to describe the efficiency of your clusters. So how many of them do you have open? How many holes do you actually have open down a hole? And in that instance, certain instances, you can glean other information from it. So for instance, if you were to have one of these rate drops occur during pad before there's any SAM, so there should be no erosion at that point, and you were to go about using the known assumptions about what hole size you're supposed to have, the number of holes you're supposed to have, and you're getting a value of, say, 120%, well, something's wrong. Perhaps your wireline company, the shots they're shooting are actually larger than what you described for downhole based on these assumptions we had made. So there's a bunch of other really interesting things you can glean from these, but the main deliverables of the analysis are really just friction of the pipe and of the perforations, and then using these things to figure out more things about what's happening downhole.
Awesome. No, this is really interesting technology, and this is interesting analysis that you've been part of. What has
Thank
this
you.
been validated against?
Yeah, so up until now, we've had the opportunity to validate the pipe friction piece in multiple basins with multiple large operators when it comes to bottom hole gauges. So basically doing what I alluded to earlier, where if you know surface pressure, you add hydrostatic, you just subtract friction in the pipe, you should be more or less with what the bottom hole gauge is reading. And then the others form of validation we've done in terms of the per friction piece was versus permanently fiber. So if the pipe friction piece is accurate, the per friction piece should be accurate as well, 'cause it's the same physics principles. And the way we went about doing that was observing when rate drops occurred on wells of permanently cemented fiber, what was our calculation lining up with what you would visually see at that given moment in terms of the flow rate going through all the clusters. So typically when the permanent fiber is saying, okay, you've got, or visually you're seeing all your clusters are taking flow rate, we're calculating 100%. And any deviation from that in terms of losing holes would be calculated by us and then visually reciprocated by the permanent fiber data. That was one way we went about validating it. And then we did a high level comparison versus the fiber uniformity index. And while uniformity, the fiber basically reports isn't cluster efficiency, it's an integral of how evenly distributed the slurry was across all the clusters for that stage. So it's not technically perforation efficiency, but you would suspect that obviously with better uniformity comes better cluster efficiency and vice versa. So the way we did that is we compared end of stage fiber uniformity, which is what they deliver, versus our end of stage perforation efficiency. And you did see a high level positive trend of like a 0.7 R squared that you would expect, given that two things aren't, again, delivering the same information necessarily exactly the same, but they should trend the right direction. And we've even gone about doing our own form of uniformity, knowing that if I have an idea of what perforation efficiency is throughout the stage, then I can go about making my own conclusions about, okay, a cluster must have shut off at this point, some more here, here's how evenly distributed the slurry would have been. And we had even better correlations with like a 0.9 R squared. We were actually taking time into account to compare it back to the uniformity index versus fiber, because that's ultimately what they're also taking into account. So that's sort of how we've gone about it now, and those are the primary validations we've done. Although obviously people ask, to compare versus step down and things like that. And again, at that point, the step down that requires assumptions about friction of the pipe and some other things. But again, obviously we're going to be in the same ballpark as that. But in all reality, ours would be more accurate in terms of we're making less assumptions to reach this conclusion ultimately. So that's sort of how we've gone about validating at this point.
That's awesome. I think the cross-validation is very important, and it really straightens the case of this analysis. So what kind of equipment is needed on the well in order to perform the analysis?
Yeah, so as I alluded to at the beginning, you really only need a high rate pressure data. So at least 20 hertz is for sure going to work. If you were, using Seismos, the company, us who invented this, we do about 4,000. But again, it's very non-invasive. Think of it just like an extra frac transducer out there that is able to observe these waves that you're sending in the well as you're going along during the treatment.
Awesome. Awesome. It's it's not as invasive. That's awesome. What was the Eureka moment that made Seismos realize that this type of analysis could be done?
Yeah, so historically, because Seismos has been around for almost a decade at this point, we've always been experts when it comes to using acoustics to tell people in oil and gas about the world around them. Like we also do work on the midstream side where we use acoustics to tell people about holes and buildup and things like that that might be in the pipeline. So we're always observing acoustics and trying to figure out what are they really telling us. And it was a few years ago during R&D discussions that someone made the observation that it'd be real nice if we could figure out friction and pipe, not just for upstream, but for midstream as well, because those are obviously that impacts a lot of the things happening operationally on both sides of the industry. And the gentleman who wrote the paper, Eric Dunham, from Stanford began to think more on it, and he realized that um, making some assumptions about what goes on at high flow rates, and knowing that at a ground level, if you have high enough sampling rate, you should see a lot of things happening in the wave to try and constrain what may be happening in the pipe and on the perforations, was able to go about doing it. So it was really just uh, again, observing problems in the world that we're heavily involved in, and then going further down the rabbit hole, and then eventually convincing an operator to like basically give it a go. Let's try and see if this actually works.
Awesome. No, this is really awesome.
Thank you.
What's the commercial value for the new deliverables for operators?
Yeah, so I think as the industry has evolved, we've gotten further and further away from the idea that what we're doing with the completion actually matters for production. Yet, if we just sit back and think about where we were 10 years ago with clusters 50, 100 feet apart, 500 pounds per foot loadings, and we noticed that as we increased volume, as we add clusters to create more fractures in the reservoir, they had certainly a positive impact on productivity. And so I still think the case still stands today that when you talk about cluster efficiency and your ability to distribute your fluid in this land as evenly across the reservoir as you possibly can is extremely beneficial commercially. Not just for the completions guy who wants to be able to treat his stages as effectively by having as many holes open as possible to pump into the reservoir, but also when you talk about other groups out there, like the reservoir engineers and the BD people who design their well spacings and their volumes, assuming that they're likely getting all their clusters stimulated sufficiently. And obviously, if that were not the case, you could end up perhaps over capitalizing. If you've got 50% of your actual clusters open, than you plan for, well, at that point, again, you're based on your well spacing and the volumes you want to pump, you're not really doing yourself a service there. Um, so I think they're all interconnected, and what do you do with that in real time? Obviously, when this information being provided, consultants can use it. They're always doing sweeps, acid, sand slugs, cutting stages short, playing with rate, because they just see there's a problem. They're not sure if it's in the pipe, if it's on the perforations, if it's from the reservoir, which in some instances might end up with them throwing a lot of things at a problem that isn't going to be solved because the things they're trying aren't meant to solve what that issue might be. Like if it's a FR problem in the pipe, well, whatever you're trying to do to open up more perfs isn't going to solve that. It's something with your FR. So that's one way, is to immediately help facilitate some of these things that consultants are doing in real time, which again, these decisions they're making in real time have a big impact in terms of pump time, productivity if they're actually opening up clusters and things like that. In the long term, I think the benefit in terms of commercial value is again honing in on these principles that we know that work. So do I have a per scheme, a cluster scheme that 90%, 95% of the time is opening most of the clusters that is matching for my well spacing the volume per cluster that I actually like to. Again, these are things that impact tens of millions, hundreds of millions, even billions of dollars, depending on the size of the operator every year. And just having assurance that all the money that you are putting down whole is acting the way you wanted it to is obviously meaningful. So I think there's the short-term benefits and the real-time aspect for some things the consultants are doing already to better facilitate their actions, and then to better facilitate the actions of the operator in the grand scheme of things. We're talking about how they're going to develop their acreage and all the things they're going to do with their design and well spacing and things of that nature.
Well, there's one more question I wanted to ask you. before I let you go. And it's a really it makes me think a little bit. What needs to happen for the industry to fully embrace the scalable frac data?
You know, at the end of the day, people do what they're incentivized to do. Um, so, you know, in business school, as you're probably aware, they always talk about the principal agency problem, where the principal has these objectives that are going to benefit him and the company and the shareholders, and the agent, typically the manager or the employee, is supposed to go about enacting them. However, obviously the agent has their own incentives and motivations to do that. And so typically in that instance, it's the agent who's at fault. But I think at this point, I really think that the people at the top, the people in the financial community, like the investment banks and things of that, they don't promote the idea that data can be helpful when it comes to the frac. Although when you look at it, it's the biggest part of the AFE. It's where we've been able to produce all of the oil and natural gas we have over the past 10 years from unlocking unconventionals. And it's not a Ponzi scheme. Like, there's a rhyme and a reason to the subsurface. And when I look at the drilling side, um, I find it very interesting that they've been able to adopt the gamma ray as a low cost real-time tool that can also be used for post-well optimization in terms of how they drill it. Yet I don't see anything like that when it comes to grabbing the fracture data from downhole. So I think ultimately for the industry to come around to it, it's just the right people in the right places pushing that message, and realizing that you know, at a low cost, I don't know, half, 0.25% of a well's AFE, the ability to learn about a frac can for sure impact the other 99.5% of the AFE, and the investments that they're putting in terms of their dollars downhole. So to me, I think that's the biggest thing, is again just the right people in the right places, pushing the message, that again, grabbing data about the frac at a way in a way that's economically feasible and doesn't impact operations makes sense.
Awesome. I'm glad you brought up the MBA.
Yeah,
Off.
yeah, people question its uses, but I've certainly used it in this conversation. I've certainly used it in others as well. So yeah, big proponent of it.
Well, thank you so much for your time, Gabriel.
Yeah, thank you, Yoshi.
Well, folks, please be sure to listen to the entire podcast interview of Gabriel Pradigo from Seismos over this SP paper. I'll also put the citation below on the description box for our viewers and listeners. This is PetroPapers, Yoshi Pradhan, and we are signing off.